Right, good morning. During this talk, you might notice some overlap with Bettina's talks, and one could attribute this to ineptitude of the presenters who did not coordinate their talks before. But it is, of course, very deliberate using learning theory that if you go through the same material multiple times, it will deepen the understanding of the material. Yeah, so. Yeah, extensions, they have, and this is basically following up on Bettina's talk, they have a very prominent pedigree in computation. Alan Turing's second paper, his first one is on something in logic. His second paper is called The Extensions of a Group. So, and the paper basically describes extension theory as you would describe it nowadays. So clearly that was very much on his mind, and this quote Bettina mentioned, this is from a proposal to get money to build a machine, where he says, yes, we can switch suddenly from calculating the levels of the neon atom to enumeration of groups of order 720.
I think, is it true that Alan Turing certainly was working at Bianchi Fourier?
Yes.
That's where he started his math career.
Yes.
Did Philip Paul also work there? I think he did, actually.
I would expect he worked there.
So he was involved in breaking codes at that
Yeah.
time.
Yeah.
Philip Paul was, let's say, very high-level researcher in group classification. That's how it came.
Okay, so let's go back to the I didn't put the dates. I can tell you the dates later. This, I think, is a pre-war paper. So this is, I think it's early 1930s. The second one is a post-war proposal to some government body to get money for building a computer in Manchester. But I can dig out the dates, yeah. So the cliffhanger from last time where I stopped. So I wanted to look at the question of a normal form in a presentation. How can we get normal forms? And in some way, this is a more general context where PC presentations could be considered as a special case from. What we are doing is we interpret relations as rules. And that, well, and this thing, what we are getting will be called a rewriting system. So really, every presentation is a rewriting system if we simply interpret these relations as rules. There are a few technical criteria. We want that there is an ordering on all the words. We want it to be multiplication invariant, multiplication compatible. We want that these rules make things smaller. The reason for it is that one then can say the process of reducing as long as possible will always terminate. We denote this by this arrow star. Reducing we can't do any longer. And there could be, well, and I should say I'm slightly sloppy here. When writing these things, you need to be careful to distinguish the group from the formal symbols and so on. I'll write them the same way, just because otherwise it's too technical. And of course, there is a problem. There is a problem that we could have an ambiguous situation that we have a word, some word which we reduce in some way, we reduce in another way, and we can't reduce further. And then clearly these are different. They are not a normal form. So we want that this cannot happen. We want that in these cases, both can reduce further again to the same word. And if we have this situation that whenever a word reduces in two different ways, they ultimately will reduce further again to the same word, then we call this rewriting system confluent. examples, confluent PC presentations. They are confluent rewriting systems. They are examples of confluent rewriting systems. And there is, and that is very much a non-trivial theorem. Well, it's not horribly long to prove, but it definitely needs a proof, which says the condition for confluence, that it works for all possible words, is actually, it is sufficient to look at overlaps of these left sides of rules. If we have an A1 and an A2 and they can overlap, we reduce in the two possible ways. We once replace A1 by B1 and then reduce, that of course will change things here, or we replace A2 by B2, changing things here. So we have two different words. These would be cases then, this would be our X and Y there. If we test that in these cases you can reduce further to the same word, then the rewriting system is confluent. And if you look at it for the special case of polycyclic groups, these then are exactly the conditions for the confluence conditions for polycyclic groups, because there the rules have as left-hand basically the pth power of one of the generators, or generators in the wrong order. G, you have a product BA maps to, if B is a lower generator, maps to A times something. Yeah? Yeah?
When you write W over X,
yes.
that means W equals X.
Okay, so that's the sloppy bit. So I have two different things. I have on the one hand the group, where I'm looking at group elements. So the arrow implies that if W is, if I look at the group element represented by the word W, that element is the same as the element represented by the word X. Yeah? But now the separate thing I have is that I'm working with formal words. Yeah? And the arrow means that I apply the rule in the word. So if I have a rule, say, a rule which says replace BA by AB, yeah? Then I can apply, so the arrow means in the word I can apply the rule and convert one word to the other.
So, okay, I see.
Yeah? Yeah? And I know this is slightly subtle, and it's just if I try to make this formal difference between them, there is no end of converting one way to another. Yeah?
And so, when you add your six to two power,
Yeah.
is that you consider a new object which consists of formal words?
Yes, yes. Yes, yes, it probably is a category, yeah. Yes, yes, yeah. And what one would need to introduce, to make it properly, you would need to introduce formal languages over an alphabet and so on. Theoretical computer science has all this mechanism, and I just didn't want to go too much into that. Yeah, but that's exactly why I said I'm sloppy here. Yeah? Okay. So, because of this criterion, there is actually a method for getting a confluent rewriting system. If we start with an arbitrary one. Why method? Well, why algorithm in inverted commas? Because this is not guaranteed to terminate in arbitrary cases. It's just if it terminates, things are fine. And the method is simply saying, well, let's look at situations where things go wrong. Let's look at overlaps of left-hand sides that reduce in two different ways. If I don't have this situation, I end up with two words which are different. If they're different, one is larger than the other, but they represent the same group element, so I add a further rule which says reduce the larger one to the smaller one. Yeah? So that will force such a situation by forcefully adding, if we don't have this, forcefully adding such a rule. And because in the group they represent the same element, that is fine. Yeah? So we are just continuing doing this. And what will happen is basically the problematic overlap is resolved by adding another rule. But because we add more rules, there will be new overlaps with the new rules. And that's why it's not guaranteed to terminate. But if it terminates, it will end with a confluent rewriting system. This method is called the Knuth-Bendix method. This is the same Knuth as with LaTeX and Robinson-Shenstedt-Knuth. In fact, Robinson-Shenstedt-Knuth basically fits very nicely in this pattern if you look at words in the plectic monoid. Yeah, Bendix was a graduate student of Knuth who, because of the Vietnam draft, left the US and went into Canada and then left academia. Yeah. Okay. And of course, this idea of we take a pair, we look at it, does it reduce nicely? If not, we add it to a generating set. This is exactly what happens in Gröbner bases. And if you go in a sufficiently formalized framework, this is basically the same as in a universal algebra context, this is the same as Gröbner basis. And you can argue or question whether Knuth and Bendix knew Buchberger's paper or not. Anyhow, so there is some technical questions about how one can convert four elements to normal form, how to do this effectively. And I think I'll skip over this because this is not really important here for us. It's just a performance question. So how do we build rewriting systems for groups? Well, the first thing I need to mention, which so far I ignore, actually this is not a process for groups, this is a process for monoids. So I can't just cancel freely, I need to consider cancellation as a particular rule. And as a pair of rules, A inverse is identity, A inverse A is the identity. And yeah, this is in principle not hard, it's just I need to keep track of inverses with extra generators, and this is a pain to implement. This is really, that's the bit which is the hardest bit of all of working with it, is to handle these inverses separately in a nice way, but from the description, basically, it doesn't matter. What we could do is we could just encode the multiplication table of the group. Yeah? So that's, if you have a finite group, that would give you some reasoning why you always have a confluent rewriting system. It's the multiplication table if you choose some normal form words for the elements. For cyclic group, it's very easy. It's you have one generator, its power reduces to the identity. For alternating groups, symmetric groups, and so on, basically one can use Coxeter presentations, and well, for the alternating groups you need to do a little bit extra, but basically that will work. For groups of Lie type and their friends, one can use the Bn pair, the fact that the Borel group is solvable and Borel subgroup is solvable and therefore has a PC presentation, and then basically use the relations of a Bn at relations which describe the Bn pair. This has been described by Schmidt in 2010. And one can even show this is not too much extra work, this is not too bad. It's not fully implemented in GAP yet, but it works so far for the cases where it's done. It works reasonably well. And so for a lot of these are of course all simple, well, we could have simple groups of order P we could have here. These are other classes of simple groups, so that we can get such rewriting systems for simple groups. Yeah?
When you say it works, are you saying is a confluent?
If you take the, yes, you need to put it into Knuth-Bendix and do a little bit extra, because the Coxeter alone does not. Yeah, and again, this is a subject where we very easily get trapped in technicalities, and I'm trying to brush them all under the carpet, which I'm apparently very successful in doing. So, to describe arbitrary groups, we need to consider them as extensions of simple groups. So let's look at extension. And as our university logo badge has extension there, I feel I'm enormously well placed to do that. Okay, so I'm talking about group extensions. I will write an extension in the form n.g. That is a notation group theorists often use. It just means I have a normal subgroup n such that the factor group is normal subgroup isomorphic to n such that the factor group is isomorphic to G. This notation does not describe uniquely a group. It's just some description of the structure. So in that form, one could write Sn as an.2. Yeah? But an cross 2 C2 could be written in the same way. It's just to describe how. So now I have, if I want to look at rewriting systems, I look at rewriting systems for both parts. So I have a generating set for n and I have a generating set for G. Now I need to define an ordering. I have orderings for words in both generating sets, but now I combine them, and I need to describe how do I combine words which are mixing both generating sets. And the way ordering is defined, that is called the Reith product ordering, is that I first ignore the n bits. I just take the G bits of both words. So I ignore the letters n, then I have a word in the G generating set. I compare these two. And afterwards, I look at the n parts as a list, and I compare the first n parts of both words. If they are different, they decide the comparison. Otherwise, I go to the next one, and so on. So that's the Reith product ordering, and it turns out in that, well, why am I using this complicated ordering? Because in this ordering, the relation BA goes to A times something makes a word smaller. That's the only reason for that ordering. Okay, and one can show this is valid with the conditions which one wants. So I have an extension. Let me briefly remind you what an extension means group theoretically. E is a group, N is a normal subgroup of E, G is isomorphic to E modulo N. I have chosen and have fixed a map from E onto G. G is a factor group, the natural homomorphism. When I talk about elements of G, in E, I typically implicitly use a chosen transversal, a map from G to E, which maps elements to representatives. In general, this transversal map is not a homomorphism. That's just the general setup for extensions. Now, how do I make rules for a confluent rewriting system for extensions? And really what I'm doing is the same what PC presentations do, just for PC. In PC presentations, The only simple factors are cyclic of prime order or cyclic of infinite order, and so the only relation I have there in the factors is x to the p. Here I have to do a little bit more. So what I'm doing is I'm looking at relations which bring words into a form first factor group representative or first factor group generators, then normal subgroup generators. So for any generator of the normal for the normal subgroup and generator for the factor group, if they're in the wrong order, I write down such a rule. And that basically describes this M I can calculate from the conjugation action of the representatives on N. And that is possible because the subgroup is normal and it is reducing because of the Reith product ordering. Then I'm taking, of course, the rules for N remain. N is isomorphic to its image in the extension. These rules just stay the same. And I'm changing the rules for the factor group by adding an N tail. If I have a rule in the factor group, this word reduces to this word. If I do the same words in representative, now the elements become representatives, this might differ by something in the normal subgroup, and this difference is sometimes called a factor system, a cofactor, a two-cocycle, because it exactly the conditions on this pair mapping AB to MAB needs to satisfy exactly the conditions for a two-cocycle. If they are satisfied, then these are all the rules one needs for describing the extension, because now every word can first be brought into a form, first a G part, first a factor part, then a normal part. With these rules, I can bring the factor part into normal form by possibly adding something different in the normal subgroup, and then everything in the normal subgroup can be brought into normal form. Yeah? So, and if the rules for N and O, this Q should have been a G, sorry, the Q should have been a G. If these rules are confluent for the normal subgroup and the factor, then this together will give me a confluent rewriting system for the extension. And indeed, here again is something one needs to verify, and I'm not doing it because it's a pain to do. But there is nothing difficult. It's just being systematic with writing such things out. So that reduces to the case of simple groups, and for those I already described how to do this. So, yeah? For polycyclic, well, Bettina defined it for polycyclic groups. I defined it for rewriting systems. Being confluent is exactly the condition that I had this diamond, that whenever I have two words I can that when I have a word that can reduce in two different ways, they will reduce to the same way. Yeah? We are using the same word because you can consider the polycyclic case a special case of this, or Bettina might say, I'm generalizing the polycyclic case. Yeah?
Perhaps, are you really generalizing it? Can you also deal with infinite groups?
Oh, okay. I think there is nothing stopping you from looking at the at infinite groups. What I apply it only in the finite case. I think you could apply it to finitely generated infinite groups.
As long as we have a confluent rewriting system?
Yes. Yes.
So the polycyclic groups give you a confluent
Yes.
rewriting system at a really reasonably cheap.
Yes, and you always have one. And I think the problem is if you look at finitely generated infinite groups, they might not, even if they are finitely presented, I don't know whether they always have a finite confluent rewriting system. Yeah?
Okay, so this here extends then to finite groups in general with confluent rewriting system, whereas the polycyclic rule is only for polycyclic groups, but also can cope with the infinite
Hmm?
This is how it fits together.
Yeah.
So a confluent rewriting system solves the word problem. Is this word W equal to this word V?
Yes.
So none of infinite.
Yes.
Yeah.
Yes. Yeah, that's one reason why you shouldn't expect it to work always. So let's look at this in an example. My extension is the dihedral group of order 18, the symmetries of a nonagon, and, well, I know I should use the Greek word for 9, which I don't remember. Anyhow. Sorry? Enya? Enyagon, oh, wow. Music. Anyhow, so we can consider this as an extension of the cyclic group of order 3, on which is actually the center of this no, sorry, it's not the center. It's a cyclic group of order 3. We have as factor group the symmetric group S3, and for this group, a confluent rewriting system is actually given by the Coxeter presentation. For S3, it happens to work. Yeah? So, I need to describe how do the generators act on the normal subgroup, and they act by inversion. Well, because conjugation, they both represent, the representatives for A and B, because they have even order, need to be reflections. So therefore they act by inversion on the cycle. Yeah? So the extension now is generated by these 3 generators. And what are my relations? Well, I have the rules for n, that is in this case just n cubed is 1, that's just copied from a rule for n. I now take rules which describe the action, so n times a reduces to a times something, and the something here is n squared. The same for b, because they both act in the same way on n. And I add tails to the existing rules. So now the rule a squared goes to identity becomes a squared goes to identity times something in n, because I've chosen representatives which have order 2 themselves. I don't need to write a tail there. You might have chosen a different representative, and then you might have to do something, but I can choose, if I choose these 2 representatives, A and B, that is the identity, that is the identity. But now if I calculate BAB and I calculate ABA, they are actually differing by n. And that comes from doing the arithmetic. So in this case, n is an element of order 3, so it's a 60-degree rotation. And if you can do the arithmetic in this dihedral group, you find out that n has to be here. Yeah? So that's confluent rewriting system for the extension. So, yeah, what can one use these for? One can use presentations and confluent rewriting systems to calculate 1 and the 2 group. And basically, I'm now telling you the same thing Bettina told you, just not for polycyclic group, but for finite groups with a confluent rewriting system. And it is basically the same method. So, 1 cocycles, they are maps from G to, oh, this should have been an N, I'm really bad in my variable name, to the normal subgroups that describe how I need to change my representatives so that the new representative system, that the new representative map is a homomorphism. Well, I can check whether the representative map on the generators is a homomorphism. That's basically von Dyck's theorem by evaluating the relators. Yeah? A map on generators is a homomorphism if and only if the images of the generators satisfy the relators. So, yeah? The transversal function is the map, so I have n embeds into the extension, it maps onto G, And now I into the extension. Yes, or a section. Yes, that's exactly the same thing. Yes. Yes, yes. Section always sounds a little bit of surgeon and yeah. Okay. So what I'm going to do is basically I consider these values of the cocycles as variables, and then by evaluating these products in the relators, that gives me equations. And why do I want that the section is a homomorphism? Because that's exactly the case for being a complement. So instead of writing this now generically, one can do it, of course. It's the thing to do if you love indices. I don't love indices. So instead of doing this, let me just show you in an example what happens. What would happen if the factor group has a relator G1, G3, G2, G1? Yeah? So now I want my new transversal, new section T prime, tau prime, to satisfy that this product is 1. Yeah? Because I'm evaluating the relator in the images. Well, what is tau prime? Tau prime is tau of G1, zeta of G1, tau of G3, zeta of G3, and so forth. Yeah? And now I'm moving the zetas to the right. I can move zeta here, just then it gets replaced by zeta acted on by tau of G3. But tau of G3, that's just the action of G3. That's the module action. So what will happen is the zeta of G1, it gets moved past tau of G3. The zeta, my normal subgroup, is abelian, so there nothing happens. It gets moved past tau of G2. It gets moved past tau of G1. So that happens from zeta 1. I get this conjugate by the rest of the word. Similarly, the zeta of G3 needs to get acted on by G2 and G1. Zeta of G2 needs to be acted on by G1, and I get zeta of G1. Okay. And now what are these zetas? These are elements of n. N is a vector. N is a vector with variable components. The action is described through matrices. So zeta of G2 acted on by G1, if zeta of G2 is a vector A, B, C, D, now I act on it with a matrix G1 and I get a vector with linear combinations of A, B, C, D. And what I wrote multiplicatively here, of course, in the module, if I look at it as vectors, I need to write this additively. And what is this? This bit is a product of representatives, which is trivial in the factor group. It will be an element of the normal subgroup. And as an element of the normal subgroup, I can also write it as a vector. And the whole thing should be the identity, which additively written is 0. So that becomes an inhomogeneous system of equations. And if I, yeah, and that's basically what I'm writing here. So I get an inhomogeneous system, linear system of equations. Its solutions give me all the ways how I can change the representatives, the section function on the generators, so that it will extend to a homomorphism. And therefore, that describes all the complements. Well, that gives, okay, and I'm saying and not equals because I'm only doing it on the generators. So this is something I can use in place of Z1. Similarly, if I evaluate B1 on the images of an n basis, I get something which I can use to represent B1, and thereby the homogeneous system of equations gives me the solution of the associated homogeneous system, gives me the one cohomology group. Particular solution of the inhomogeneous system gives me one complement. And then if I have one complement and the one cohomology group, I can describe all complements. Yeah, but what I'm doing here is, and again, that might be too formal, it's almost just as a warning, I don't have necessarily the full Z1. I have a Z1 only given on generators with a convention that the values of the cocycles on other elements are as if the section map is a homomorphism. So take the normal form of that element, the value of tau on a product AB is defined. I'm using this and say this will always be the product of tau of A times tau of B if an element is given by the normal form AB. The one cohomology. Yeah. For the cohomology, it's an injective map. For one, it might still work. For two, it's, yeah. Okay. Yeah, yeah.
You don't really need the section, you just need the action of the module. And then, of course, an action of the module is going to be...
Yes, for the one, yeah. For the, so this slide should have gone to the two. Okay, the K would be 1 or 2. Okay, then, so after this, let's go to Geproad and look at this in a concrete calculation.
Which state is that in?
Colorado.
Is that in Fort Collins?
No, it's not in Fort Collins. It's a little bit south of Boulder. There is, I know you have a gap. There was I saw a bus which had gap on the front, and I tried to take a picture, but the way they have the display, it reflects. If you take a picture, actually, you don't get the display properly. Yeah, yeah. So.
Take a long ISO picture.
Yes. So. I'm taking some group here of order 960. Yeah, it has an A5 as a factor, and then the radical has order order 16. I calculate the one cocycles for the action of this group on its radical. The radical here turns out to be elementary abelian, which I verify. I calculate the one cocycles. And what I get is basically vector spaces, and there is a subspace 1 cocycles, a subspace 1 coboundaries. If I calculate a basis for a complement vector space that describes the factor, I get this spaces here. And how is this to be read? So first this tells me I have a two-dimensional vector space over the field with two elements. So I will have 4 conjugacy classes of complements, and that's indeed what I would find if I look at conjugacy classes of complements. And the way it's to be read is I have two generators for my group, this generator and for the factor group. These are elements which represent the factor group. So this is tau on the two generators. I have a four-dimensional vector space underneath. So these are in, this is one vector, this is second vector, and that first bit is for the first generator, that bit is for the second generator. So in fact, the one cohomology doesn't do anything for that chosen first generator, it just changes something for the second generator. Yeah? That's how we can read this. If you want to do something more elaborate, in there actually are functions, list to cocycle and cocycle to list, which take a list of normal subgroup elements and convert to vectors, or even if you have a particular complement as a subgroup, there is complement to cocycle and cocycle to complement, which take, say, a cocycle and give you the corresponding complement, or vice versa, take a complement and give you the corresponding cocycle. Okay, that's one cohomology. Now, and I just, in case this was too easy, two cohomology. What I now want to do is I want to ask, if I have given n and g, can I construct an extension which has the form n dot g, which has a normal subgroup isomorphic to n and a factor group isomorphic to g? So I want to write down relations of this. I assume I have confluent rewriting system for n and for g. I want to combine them by adding these these extra gluing relations and adding tails. If I do this randomly, the n part might collapse. I always will get g, but I might not get n. But I will get the structure if the if this extended presentation or the rewriting system is a confluent rewriting system. So what I'm going to do is I consider the tails added to the relations of the factor group. I consider the tails as variables. And I use the, oh, and that is not Z1 but Z2, sorry. This should be a 2 in both cases. I use the tails, I use the tails as variables, and then the confluence conditions will give me equations I can write as linear equations in the tails, in a similar way as I've done before.
In the implementation,
Yeah.
is there any way when you're doing kind of finite search, I mean, if this is an infinite group, is there anything that you do which says that I only have a finite choice?
Well, I'm using it for finite groups. I'm assuming that my factor group G has a finite confluent rewriting system.
Oh no, but you could have an infinite group with
If I have an infinite group with a finite confluent rewriting system, I think that will go through exactly in the same way, and I don't need to do, it's still a linear system of linear equations. And what happens here is now that I only give, and that's where I should have had this slide with a warning. Now I don't calculate all of Z2 because I'm only giving the value of tails for the relation on the factor. And I'm assuming I'm using the normal form to represent other elements. So therefore, I have a restriction on what is actually possible for my section or how my section is defined. And what I just get is enough that the quotient modulo the image of B1 in there gives me the two cohomology group. So again, let's look at it in an example. The same example as before. Factor group S3, normal subgroup C3, both generators act as -1. Yeah? So the factor group relations get tails which are variables, a variable x, a variable y, a variable z for these three relations. Now, and of course, I keep the relations for n, and I add the relations how the factor acts on n. I didn't write these out. Now, overlaps. Yeah, I need to look at possible overlaps of left-hand sides. So the word A3 can be written as considered as an overlap of the rule A square with itself. So I have these two ways of reducing it. Here I reduce it to AX, here I reduce it to XA, which with the action becomes AX inverse. Canceling A tells me X inverse has to be equal to X. Similarly, if I do the same with B, because I have there the same situation, I get that Y is equal to Y inverse. Now, let's look at BAB square. That's an overlap of BAB with B square. Yeah? I can reduce it by reducing B square using this rule to Y, then it becomes BAY. Or I can reduce BAB to ABA, getting Z here times B, moving the Z past the B inverts it. Now I have here again a BAB, which becomes an ABA, reducing A squared, so I get, at this point, BAX. Well, this gives me X is Y, and similarly, by overlapping with A, I get Y is equal to X. Since they're both 0, this is not something new. And if I look at the overlap of BAB with itself, that would be BABAB, I get basically in these cases I get this equation here, and because I know that X is equal to Y, that just gives me equation Z is Z, so no restriction on Z. So my solutions are the vector space of vectors 0, 0, Z. So my 2 cohomology has order 3 because I'm over the field with 3 elements. I know already that there is a non-split extension, namely this dihedral group. So the dimension of H2 really must be 1, as I have found here. It can't be bigger because I have only one variable here. So again, in GAP, here I'm taking the symmetric group as 4. I calculate the irreducible modules of this group over GF2. I take the second of them that has dimension 2. And now I calculate the 2 cohomology this way. Yes, the names for the cohomology functions and the way they work in GAP is slightly awkward in that there is a version for finite PC groups, there is a version for polycyclic groups, possibly infinite, and there is a version for arbitrary finite groups using rewriting systems. There are 3 different functions with slightly different syntax and output, because really the algorithms do things like use slightly different things. Yeah, so what it gives me is it uses from the monoid rules which are used. Some don't need to be used because they basically just describe inverses. I have 1, 2, 3, 4, 5, 6, 7 rules. My subspace, the module is 2-dimensional, so I get vectors of length 14, 7 times 2. And now there is a function FP group cocycle. It gets the cohomology record. The vector in the cohomology I want. So that is a 1 by 14 matrix. The cohomology is 1-dimensional. So each row is a basis vector. I just take that basis vector. I could have taken its negative and get another extension. This last true tells it, don't just write it as a finitely presented group, but try to get a permutation representation that is sometimes nicer to continue work with. and it gives me this group on a generating set, which is ABC is the generating set of S4. These are the generators of the module. And I can look at the relations, and I can basically trace through in these vectors of length 14. There are 7 entries of length 2, and they correspond to these 7 relations. So if I look at the, so which relation did I pick? If I look at the relation CA maps to AC, that is in position 4 of those. These I don't need to count because they just handle the inverses. Yeah, that is in position 1, 2, 3, 4. So that will be the 4th component here, which is 0, 1. And that gives me the relation that if I write this as, consider the rules as relators in the form left inverse right, so I get A inverse C inverse AC. Before becomes the identity, now is M1 to the 0 times M2 to the 1. Yeah? That's the translation between cocycles and
And if you've given it a polycyclic group generated by polycyclic generators, would the relations look like power commutator?
well, I mean, there are the commutator, the idea, they are always written down basically like the commutator relations. It's just here it lives in the rewriting system world. Yeah, but it would be basically, yeah. Yes, it would be relations which they are not as data type, they're not polycyclic relations. Mathematically, they are polycyclic, yeah. Okay, that I don't need. Let me skip how I get the permutation representation. So, brief application is to actually investigating finitely presented groups. Class of algorithms I mentioned on Tuesday, quotient algorithms. They take a finitely presented group and try to find the largest quotient in a certain class. And what they do is basically, there is already an existing quotient. We try to make the quotient bigger by putting a module underneath. Why only a module? Because we can assume with a solvable radical data way of looking at it that everything non-solvable is there at the start. And we want that we have new homomorphism where the kernel is smaller, and this factor of the kernels is just the module for the fact, and we want the new kernel to be as small as possible. And the way it is done is we start with the existing homomorphism, we choose a module, we form all extensions, or even one can in many cases define a universal cover for this type of module. That uses cohomology to construct this cover. We evaluate the relators in this universal cover. The quotient modulo the evaluated relators gives us the largest quotient. And this has been done for P groups. That's the P quotient algorithm. There, this cover is called the P cover. It has been done and in gap epimorphism P group or the ANU-PQ package implement this. Finite solvable groups, probably the most prominent by Pleskin, implemented through epimorphism solvable quotient. And now we can also do it. This is recent work of Heiko Dietrich and myself, using these ideas for cohomology for finite groups as long as the radical factor doesn't get bigger. So the non-solvable bit stays the same. This is currently implemented only in GitHub. Let me encode on GitHub. Let me just finish by showing you this in an example because I'm very proud of this. I take a finitely presented group. This is one which is called the Heineken group, not because of the beer, because of the mathematician. Yeah, this becomes basically, oh, here I think of some brackets are here brackets are missing around. Sorry. No, sorry, there aren't brackets missing. Sorry, this is commas. So I have 3 relators, and they are a little bit, let's just play around what happens with iterated commutators. I calculate the quotients to the alternating group of degree 5. There is only one of them. I take the first one, so there is a homomorphism to A5. And now I want to lift with modules characteristic 2. If I'm doing this the first time, it lifts, basically it calculates all the modules in characteristic 2. There are 3 of them for A5. For each of them forms a cover, and then of this cover for dimension 1 would have order 480. The cover for this module would have this order, and so forth. But not all of the cover actually is compatible with the relators, only part of it. And what I end up is I get extended by a 1-dimensional module and 4-dimensional module. So I have dimension 5. If I run it again, what is underneath is a 2 to the 6. If I run it again, I get up to a 2 to the 24 underneath, and then it stops. This whole calculation takes about a minute on my laptop.
So why does it stop?
Because there isn't any larger. Underneath that A5, I cannot put any larger 2 group such that it is compatible with these relations. Yeah? I have calculated another way how I could have calculated this. I could have rewritten the presentation to the kernel of the map onto A5 and ran a p quotient on the kernel. And the largest 2 quotient there is of order 2 to the 24. And why is it 2 to the 24? That follows from these relations. There is no easy answer why this is the case. Yeah? And the range, this map is a homomorphism. This is a group. It is actually represented as a formal extension in a similar way as PC presentations, because the smallest permutation degree which would be possible would be about 130,000, and then the calculations would be far too slow. Yeah, and I'm, I think, more than out of time, and we are reaching the holy 12:30. Thank you very much.